There is a single rule written quietly into everything you have ever touched. It says that no two identical particles of one particular family can ever occupy the same quantum state. Physicists call it the Pauli Exclusion Principle. Here is the figure that should stop you where you sit. An atom is more than 99.999996% empty space by volume. Shrink an atom in your mind until its nucleus is the size of a pea. The rest of it, the whole electron cloud, would fill an entire football stadium. A pea at the centre and a stadium of near-perfect emptiness around it. That is what your hand is made of. That is what the table is made of. And yet you cannot push your hand through the table. That is the strange thing we're going to sit with tonight. Your body is mostly empty space. The table is mostly empty space. Two clouds of almost nothing meet, and one flatly refuses to pass through the other. Something is holding the line, something invisible, silent, and completely reliable. The ordinary story you were probably told is simple. Things feel solid because they are full of stuff. Wood is dense. Steel is denser. Your finger meets the wood is packed tight so it stops. It is a comfortable picture, and it is almost entirely wrong. There is barely any stuff there to begin with. The solidity you feel is not the fullness of matter. It is the enforcement of a rule. If this is the kind of quiet, strange physics you like to fall asleep to, a soft tap on the like button and a follow help more than you know, and every one of these is on Spotify too if you drift better with just the voice. That is the only time I will ask. Now settle back. Let us start with the man who wrote the rule down. His name was Wolfgang Pauli, an Austrian physicist with a reputation for a sharp tongue and an even sharper mind. In January of 1925, he put forward a short, strange idea that would end up explaining the shape of the entire physical world. He was not trying to explain white dwarf stars or why your floor holds you up. He was trying to fix a much smaller and more embarrassing problem. The best model of the atom at the time simply did not work. That model belonged to Niels Bohr. Bohr had pictured the atom as a tiny solar system. A dense nucleus sat at the centre, and electrons circled it in fixed orbits, each orbit a rung of energy. It was elegant, and it explained a great deal. But it had a hole in it that no one could patch. In physics, systems fall toward their lowest energy. A ball rolls to the bottom of a bowl. Water runs downhill. So every electron in every atom should tumble down to the lowest orbit, the rung nearest the nucleus, and stay there. If that were true, every atom would look almost the same. All the electrons would pile into the bottom rung together, a crowd pressed against the floor. There would be no rich ladder of energy levels. There would be no chemistry worth speaking of. There would be no reason for one element to behave differently from another. And yet the world is full of difference. Gold is not helium. Oxygen is not iron. Something was stopping the electrons from all falling to the bottom. Pauli's answer was almost insolent in its simplicity. Nothing pushes the electrons apart with a force. Nothing holds them up. There is simply a rule, and the rule is a refusal. No two electrons in an atom, he said, can ever share the same complete set of quantum numbers. Each electron must have its own unique address. Once the bottom rung is full, the next electron is forbidden from joining, not discouraged, forbidden. It has no choice but to take a higher rung instead. To feel what that means, you have to know what a quantum address actually is. An electron in an atom is described by 4 numbers, and together they pin down its state completely. Think of them as a street, a house, a room, and a final tiny label on the door. The first number is called the principal quantum number, written as n. It sets the shell, the main energy level, roughly how far the electron sits from the nucleus. You can picture it as the street the electron lives on. The higher the number, the further out the street, and the more energy the electron carries. The second number is the angular momentum quantum number, written as L. It sets the subshell, the shape of the region the electron occupies. Some regions are round like a ball, others are stretched like a dumbbell, or shaped into stranger lobes and petals. If n is the street, L is the particular house on it, and each house has its own form. The third number is the magnetic quantum number, written as m sub L. It sets the orientation, which way that shape is pointed in space. A dumbbell can lie along one axis or another. This is the room inside the house. Together, a shape and an orientation define a single orbital, one specific pocket of space where an electron is allowed to be. And here is where you would expect the story to end. One orbital, one electron. But nature slips in a fourth number, and it is the strangest of them all. It is called spin, written as m sub s. Spin is a property with no real match in the world you can see. The name is a trap. The electron is not a tiny ball turning on an axis. Nothing is physically rotating. Yet mathematically, the electron behaves as though it always points in one of exactly two directions. Call them up and down. That is the whole of it. A binary label, a single flipped switch on the door, that one extra switch changes everything. Because spin has two values, a single orbital, one shape pointed one way, can hold not one electron but two. One with spin up, one with spin down. Their first three numbers match perfectly. They share the same street, the same house, the same room, but that final switch is set differently, so their full addresses are not identical, and the rule is satisfied. Two electrons can squeeze into one orbital, and only two, and only if their spins are opposite. Try to force a third electron into that same orbital, and there is no address left for it. All four of its numbers would have to copy an electron already there. The rule forbids it. So the third electron climbs to the next available orbital, and the fourth climbs higher still, and the electrons stack upward through the shells like water filling a set of narrow shelves rather than pooling on the floor. Picture two people trying to stand in the exact same footprint, at the exact same moment, facing the exact same direction. It cannot be done. One of them has to move, has to turn, has to find a different place to stand. That is the exclusion principle in a single image. Not a shove, not a wall, just a quiet, unbreakable impossibility of two things being in precisely the same state at once. This is why the periodic table has the shape it does. The whole grand chart on the classroom wall is really a map of these filling shelves. Each element has one more electron than the last, and that electron has to go somewhere new. Sometimes it lands in a snug, complete shell, and the atom sits calm and unreactive. That is neon, or argon, a noble gas that wants nothing to do with anything. Sometimes it lands alone in a fresh, nearly empty shell, loosely held and eager to leave. That is sodium, a soft metal so restless it bursts into flame when it meals water. The difference between an inert gas and an explosive metal is nothing more than where the outermost electrons were forced to sit by this one 1925 rule. Every property of every element you have ever heard of traces back to the same quiet refusal to share an address. Pauli, at first, was cautious about how far his idea reached. He had written it for electrons inside atoms, and that is where he left it. But the rule turned out to be far larger than the problem it was invented to solve. Over the following years, it became clear that this refusal was not a quirk of electrons in atoms. It was a property of a whole class of particles, wherever they were found, in a star or in your fingertip or in the empty dark between galaxies. In 1940, Pauli tied the whole thing to something deeper, in what is now called the spin statistics theorem. It sorts every particle in nature into two great families by that spin number. One family has spin measured in halves, a half, or 1.5, and so on. These are the fermions, and they include the electron, the proton, the neutron, and the quarks that build them. Every fermion obeys the exclusion principle without exception. No two identical fermions may ever share a quantum state. They are the loners of the universe, each insisting on its own address. The other family has spin measured in whole numbers, 0 or 1 or 2. These are the bosons, and they include the particles of light. Bosons obey no such rule. They are perfectly happy to pile into the same state by the thousands, the millions, all singing the same note at once. That is why a laser can exist, countless particles of light marching in perfect step. The universe is split down the middle by a single number. Halves keep to themselves. Wholes crowd together. Your solidity, your shape, the fact that you take up room at all, comes down entirely to the fact that you are built from the loners. Pauli was given the Nobel Prize in Physics in 1945 for the exclusion principle, and the nomination came from Albert Einstein himself. It is worth pausing on that. The most famous physicist of the age put forward Pauli's name for a rule that says, at its heart only this. Two identical loners cannot stand in the same place. Einstein saw how much of the world hung from that single thread. There is one more thing to hold before you drift, and it is the strangest of all. After a century of testing, after the principle has proven itself in every atom and every star, no one can tell you why it is true. Physicists can show that it follows from the deep mathematics of quantum field theory, from the demand that the universe stay consistent with relativity. The proof exists. But a proof is not an explanation you can feel. Richard Feynman, one of the clearest minds physics has ever produced, admitted openly that he could not give a simple, intuitive reason for it. He could not tell you, in plain words, why spin and this refusal must be locked together. It simply is. The rule holds, flawlessly, everywhere, and its deepest why remains just out of reach. So the picture is this: a quiet Austrian physicist trying to patch a broken model of the atom wrote down a single sentence in the winter of 1925. No two identical fermions may share the same quantum state. From that one sentence flows the entire periodic table, the whole of chemistry, the reason a floor is a floor and a hand is a hand. It is not a force. It pushes on nothing directly. It is closer to a law of etiquette that the universe enforces without ever bending, a border no particle has ever been caught crossing. And it is happening inside you right now, trillions upon trillions of times over, in every atom of your skin resting against these sheets. Each electron holds its own address and lets no other take it. That single refusal, one electron quietly declining to share an address, is the reason anything you touch pushes back at all. That single refusal, one electron quietly declining to share an address, is the reason anything you touch pushes back at all. Hold on to that thought and press on it. Try to crowd those electrons together, squeeze them into a smaller box. You might expect them to grow calm as the space shrinks, to settle. They do the opposite. They speed up, they climb. Here is the mechanism, slowly. Every electron in a confined space has to occupy its own quantum state. The low, comfortable states fill first. Once those are taken, the next electron has no choice. It cannot drop into an occupied address. It must take a higher one with more energy and more motion. Press the box smaller, and more electrons are forced up the ladder. The whole crowd grows more frantic, not because it is warm, but because it is trapped. That frantic motion has a name. It pushes outward on the walls of its own box. Physicists call it degeneracy pressure. It is a real, measurable outward push, and it comes from nothing you can point to. No fire heats it, no fuel feeds it. It does not care whether the matter is hot or cold, which is one of the strangest things about it. It exists purely because the exclusion principle forbids the electrons from all sinking to the bottom together. The tighter you squeeze, the harder it shoves back. That single fact will carry the rest of tonight a very long way. For now, keep it close to home. You do not need a collapsing star to meet this pressure. You meet it every time you rest your hand on something. Slam your palm flat on a table. In the ordinary story, your hand hits the wood and stops. But nothing in that collision actually touches, not in the way you imagine touching. Between the atoms of your palm and the atoms of the wood, there is only empty space and the fields that fill it. What stops your hand is trillions of electron clouds being forced toward overlap, and the exclusion principle will not permit the overlap. It pushes back like an invisible spring, and that push, multiplied across every point of contact, is the hardness you feel. The tabletop is not stopping your hand. A rule is. You have probably heard this explained a different way. Simple electric repulsion, the story goes. Like charges repel, so the electrons in the table repel the electrons in your hand, and that is why solids do not pass through each other. It sounds obvious. It is mostly wrong. An atom is electrically neutral. Its negative electrons and its positive nucleus balance out to zero. Stand two neutral atoms a short distance apart, and there is no strong net electric force between them. The charges cancel. Charge alone cannot explain why the table holds your weight. The real resistance is the exclusion principle acting on those overlapping clouds. Physicists call it exchange repulsion, or Pauli repulsion. It is not the ordinary shove of like charges. It is the flat refusal of two identical electrons to enter the same state at the same place. That refusal is the wall your hand runs into. Solidity, it turns out, is not a touch. It is a denial. When you knock on a door, you're hearing a rule enforce itself over and over faster than you can follow. For a long time, this was intuition rather than proof. Everyone could feel that matter was solid. Everyone could feel the invisible spring. No one had actually shown, from the mathematics alone, that the exclusion principle was strong enough to hold the whole, vast structure of ordinary matter up. That gap stayed open for decades. It closed in 1967. Two physicists, Freeman Dyson and Andrew Leonard, published a long and difficult paper in the Journal of Mathematical Physics. They proved rigorously that the exclusion principle among electrons is what makes ordinary matter stable against collapse. Not approximately, exactly. The refusal is the reason a lump of matter settles at a fixed size instead of shrinking without end. Double the amount of matter and you get roughly double the volume, which sounds too simple to need a proof. It needed one, and the proof was hard. It was so involved that very few people worked all the way through it. So 8 years later, in 1975, two more physicists found a cleaner route to the same summit. Elliot Lieb and Walter Thirring built a simpler argument, resting on a mathematical result now known as the Lieb-Thirring inequality. Less labour, same destination. Matter is stable because fermions refuse to share. That is not a slogan. It is a theorem. There is still a quiet mystery folded inside it. The exclusion principle lives, in the deep mathematics, in something called an antisymmetric wave function. That particular form is the one nature chose. Why that form, rather than some other rule that would also be consistent, no one can fully say. The proof tells you the refusal holds the world together. It does not tell you why the refusal exists. You can rest tonight knowing the floor is stable and knowing that even the people who proved it cannot explain, at the deepest level, why. Now ask the darker question. These proofs do more than show that matter is stable. They show, by implication, what would happen if it were not. This is where the calm arithmetic turns cold. Switch off the exclusion principle, only in your imagination, only for an instant. The electrons lose their reason to stay apart. Nothing holds them on the higher rungs of the ladder. All of them cascade down toward the lowest orbital at once, every electron in every atom trying to occupy the same comfortable state. The atoms deflate. The empty space that made up almost all of their volume simply folds away. Matter falls inward, plunging toward nuclear density, the crushing density of the atom's tiny central core. And a collapse like that cannot be gentle. All those electrons giving up all that energy have to release it somewhere. Dyson and Leonard estimated the scale of the release. Bring two ordinary objects together in a world without the exclusion principle, two things no more remarkable than your two hands, and the energy let loose would be comparable to an atomic bomb, not from any nuclear reaction you would recognize, just from matter finally being allowed to do what gravity and electricity always wanted it to do, and fall. That is the hidden violence under the quiet. Every time you clasp your hands, the exclusion principle is holding back a detonation you will never see, because the rule has never once failed. The bomb stays disarmed because two electrons will not share an address. Sit for a moment with what that means for the ground beneath you, and here, past the hard first stretch of the night, you can let this next part settle over you slowly. You are far emptier than you feel. An atom is more than 6% empty space by volume. Almost all of its mass hides in the nucleus, which fills roughly 1 part in a quadrillion of the atom's room. Scale a single atom up until it is the size of a football stadium, and the nucleus would be one small pea resting at the very centre of the field. Everything else, all those rows of empty seats, is electron cloud. An electron cloud is very nearly nothing at all. Your body, the chair, the floor, the whole solid world is built from these vast pockets of vacuum, yet you do not sink through the chair. The floor does not swallow your feet. Your own bones keep their length and your skin keeps its edge. Every bit of that rigid architecture is mostly empty, held open from the inside by electrons that will not share a state. That is the whole trick. The solid ground you trust with your entire weight is a scaffold of refusals. Take the refusals away for a single second, and the picture is grim. The floor and your body would both collapse toward that P at the centre. All the emptiness would vanish. What remained of you, of the room, of everything in it, would be smaller than a grain of sand. And it would not go quietly. It would go with the flash Dyson and Leonard calculated, the energy of falling matter set free. So the next time you lean back and the surface holds, notice what is actually happening. Nothing is touching. A thin invisible pressure, born of pure quantum crowding, is pressing back against your weight with exactly enough force and not one bit more. It asks for no fuel. It never tires. It has been pushing back in you and in the ground for as long as you have existed, and it will keep pushing back long after. You have spent your whole life resting on a rule, and it is the same rule everywhere, at every scale. The pressure that keeps your fingertip from sinking into your fingernail is not a special local effect. It is the identical stubbornness that fills a boulder, a mountain, a planet. Wherever electrons are pushed together, the same refusal answers with the same outward pressure. Usually it is a background you never notice, quiet and effortless, holding the shape of small things. But that pressure has a ceiling, and gravity knows exactly where it is. On a world like ours, the crowding is mild and the electrons barely stir. Pile on enough mass, though, and gravity begins to squeeze in earnest. The electrons are forced higher and higher up the energy ladder. Their quantum motion climbs until they are racing at a real fraction of the speed of light, still stone cold, still driven only by the refusal to share. The push grows immense, and for most of the universe, that immense push is more than enough. Ordinary stars, planets, moons, all of them sit far below the point where the rule could ever be in danger. For thousands of years, the star Sirius was simply the brightest point in the night sky. You can still find it yourself on a winter evening, low in the south, burning white and steady. People watched it for millennia and saw nothing strange about it. Then, in 1844, a German astronomer named Friedrich Bessel noticed something that should not have been there. Bessel was one of the most careful measurers who ever lived. He had spent years tracking the exact positions of stars night after night, writing down where each one sat against the dark. And when he studied Sirius closely, he found that it would not hold still. The star was drifting. Not in a straight line, the way a distant star should, but in a slow, gentle wave. Picture a single dancer moving across a floor. Instead of walking a straight path, the dancer sways from side to side, leaning one way and then the other, as if held in the arms of a partner. But the floor is empty. There is no partner. There is only one dancer, swaying to the pull of a hand that no one can see. That was Sirius. It wobbled as though something were tugging on it, first from one side, then the other, over a slow rhythm that stretched across decades. Bessel understood what that meant. A wobble like that comes from gravity. Something massive had to be circling Sirius, close enough to swing it back and forth as the two of them orbited a shared centre. Here is the strange part. Bessel searched for that companion and could not find it. He had the finest instruments of his age, and the patch of sky where the hidden partner should have been was simply dark. So he did something bold. He announced that an invisible star was there anyway. He could not see it, but he could feel its weight in the motion of the star it pulled. He had found a body no one could observe by watching what it did to its neighbour. For 18 years, the dark companion stayed hidden. It might have stayed a rumour forever, a clever guess drawn from a wobble, if not for a lens. In 1862, an American telescope maker named Alvan Clark was testing a new instrument. Clark built some of the finest lenses in the world, and he had just finished the largest one he had ever ground. To test it, he pointed it at the brightest star he could find, which was Sirius, and there, sitting close beside the blazing star, was a faint speck of light. At first he must have thought it was a flaw, a smudge in the glass, a stray reflection, some ghost of the bright star bleeding across the lens. But the speck stayed put. It was real. It was exactly where Bessel's arithmetic said the hidden partner should be. Clark had become the first human being to actually see the invisible companion, a dim ember beside a bonfire drowned out for 18 years by the glare of the star it orbited. They called it Sirius B. The bright star became Sirius A, and for a while that was the whole story. A faint companion, found first by mathematics and then by glass. It seemed like a small, dim, unremarkable little star. The real shock came later, and it came from the light itself. By 1915, astronomers had learned to read a star by spreading its light into a spectrum, splitting it into colours the way a raindrop splits sunlight. Those colours carry secrets. They tell you how hot a star's surface burns. And when astronomers finally caught enough of Sirius B's feeble light to read it, the numbers made no sense. The little companion was hot. Ferociously hot. Its surface glowed near 27,000 K, far hotter than the surface of our own sun. A surface that hot should pour out an enormous flood of light. Yet Sirius B was dim, almost absurdly dim for something burning so fiercely. There is only one way to be that hot and that faint at the same time. The star had to be tiny. If every patch of it blazed like a furnace and the whole star still gave off so little light, then there could not be much surface to it at all. The astronomers ran the numbers, and then they ran them again because they did not believe them. Sirius B was roughly the size of the Earth, and yet the wobble had already told them its weight. To swing a star like Sirius through its slow dance, the hidden companion had to carry nearly the entire mass of the Sun. So here was a thing with the mass of a star crushed down into the volume of a planet. Work out what that means for its density, and the answer becomes almost frightening. Sirius B was packed roughly 400,000 times more tightly than the ground you're lying on. A single scoop of it, small enough to cup in your hand, would weigh as much as an elephant. Matter simply was not supposed to do this. Nothing in the physics of that era could explain it. A normal star holds itself up by burning. Deep in its core, fusion pushes outward, a furnace forever fighting gravity's endless squeeze. Take a heavy weight and set it on a spring, and the spring pushes back. That is a living star, its fire pressing out against the crush of its own mass. But a star this small and this faint had no furnace left. Its fire had gone out. It was, in every sense that matters, a dead sun. The spring should have had nothing left to push with. So what was holding it up? Gravity should have kept on crushing it. With no fusion pressing back, nothing that anyone understood should have stopped Sirius B from shrinking, and shrinking again, and collapsing down toward a single point. And yet there it sat, steady, the size of a planet, refusing to fall any further. The astronomers had found a body that broke their physics. They could measure its weight, its heat, and its impossible density, and they could not name the force keeping it whole. They had a dead star that should have collapsed and simply had not, and no honest way to explain why. The answer would not arrive for another decade, and when it came, it would not come from the study of stars at all. It would come from a rule being written about the smallest things in nature. A rule about how electrons are forbidden from ever crowding into the same address, and how that single refusal is what gives ordinary matter its shape and its stubbornness. It is the same quiet refusal, working in you right now, that keeps your own hand from sinking straight through the surface you're resting it on. But there is a place in the sky where that same stubborn pressure is the only thing standing between a dead star and total collapse. But there is a place in the sky where that same stubborn pressure is the only thing standing between a dead star and total collapse. Picture a star like our sun after the fire goes out. For billions of years it held itself open by burning, fusing hydrogen into helium, pouring heat and light outward against the crush of its own weight. Then the fuel runs low, the fusion stutters and stops, and now nothing is burning at the centre of that star at all. By every rule you might expect it should fall inward. Gravity never rests. It keeps pulling every ounce of that star toward a single point, and the fire that once pushed back is gone. So the star does fall. It shrinks and shrinks, until it is no longer the width of a sun but roughly the width of the Earth. And then, astonishingly, it stops. A whole star's worth of mass, packed into a ball you could fit between the Earth's poles, simply holds, not warm, not burning, just held. What holds it is the same rule that gives your own body its shape. The electrons inside that dead star refuse to share the same quantum state. As gravity squeezes them closer, they are forced into higher and higher energy levels, and that refusal becomes a real outward pressure. Physicists call it electron degeneracy pressure. It has nothing to do with heat. You can cool this pressure to almost nothing, and it does not fade, because it was never made of warmth. It is made of quantum law. If this is your first night drifting off with us, a quiet like or subscribe helps more people find these long, slow walks through the physics of everything. We are on Spotify too, if you would rather listen with your eyes closed. That is the only thing we will ask of you tonight, so hold that strange object in your mind, a star that has died and yet does not collapse. We call it a white dwarf, and the numbers inside it are almost impossible to feel. Start with the density. The first white dwarf ever found is a small companion to Sirius, the brightest star in our night sky, and we call it Sirius B. Its story began with a wobble. In 1844, the astronomer Friedrich Bessel noticed that Sirius seemed to sway ever so slightly as it moved, as if something unseen were tugging on it. He could not see the companion, only its pull. Nearly 2 decades later, in 1862, the telescope maker Alvan Clark turned a new lens towards Sirius and found the faint point of light that had been hiding in the glare all along. For 50 years, no one understood what it was. Then, in 1915, astronomers measured its light more carefully. Its surface glowed at around 27,000 Kelvin, far hotter than our own sun. A surface that hot should be blazingly bright, yet Sirius B was dim. The only way to be that hot and that faint is to be very, very small. When they worked out its size, they found something close to the size of the Earth, and when they worked out its mass, they found something close to the mass of the Sun. Put those two facts together, and the number that falls out is staggering. Sirius B has a density of roughly 2.7 billion kilograms packed into every cubic meter. That is about 400,000 times denser than the Earth beneath your feet. At the time, no one could explain it. It looked like a mistake in the arithmetic of nature. Try to feel it another way. Imagine you could scoop a single teaspoon of white dwarf material and set it on your kitchen table. That teaspoon would weigh somewhere around 5 to 5.5 tons. That is roughly the weight of a full-grown elephant resting on a spoon. You could not lift it. No table could hold it. It would punch straight through the floor and keep going, because ordinary matter is mostly empty space, and this is matter with the emptiness wrung out of it. Now go inside that star, down where the pressure lives. The electrons there are not drifting lazily between atoms the way they do in the metal of your spoon. They are jammed together, packed shoulder to shoulder in a room that keeps shrinking around them. And here is where the exclusion principle shows its hand. Two electrons cannot occupy the same quantum state. When you crowd them into a tiny volume, they cannot all settle into the same low calm energy. They are forbidden from it. So they are forced to climb, filling one energy level after another, all the way up. Some of those electrons end up moving at speeds approaching the speed of light. And they are not moving that fast because the star is hot. They are moving that fast because they have nowhere left to go. It is not heat. It is pure quantum claustrophobia, a frantic motion born entirely of the refusal to share an address. That frantic motion is the pressure. Every one of those speeding electrons pushes back against the squeeze, and together they hold up an entire star. Think of it as a room packed so full that the walls cannot close any further, not because the people inside are warm, but because there is simply no legal place for one more body to stand. That standing room, multiplied across every electron in a dead sun, is what keeps a white dwarf from falling into itself. And for a long time, people assumed this trick would always work. If a star could hold itself up this way, why would any star ever do anything else? Surely every star, no matter how heavy, could shrink down, crowd its electrons, and settle into a quiet white dwarf forever. That was the comfortable assumption. It was wrong. The person who broke it was almost a boy. In 1930, a 19 and 20-year-old student named Subramanian Chandrasekhar boarded a ship in India, bound for England to begin his studies at Cambridge. The voyage took weeks. The ocean between Madras and Southampton is slow, and there was little to do but think. So he thought about white dwarfs, with a pencil and paper, and the long empty days of the crossing. He asked a simple question. What happens to that electron pressure when the electrons are moving almost as fast as light? Because there is a catch built into the universe. Nothing can move faster than light. As you squeeze a white dwarf harder and its electrons speed up, they begin to bump against that cosmic limit. And once they do, they can no longer push back any harder, no matter how much you squeeze. Their speed has run out of room to grow. When Chandrasekhar folded that fact, the fact of special relativity, into the mathematics of degeneracy pressure, a number fell out that changed astronomy. He found a ceiling. He found a maximum mass above which the electron simply cannot win. Below it, the star holds. Above it, the pressure gives way, and gravity keeps pulling, and there is nothing left to stop the fall. That ceiling sits at about 1.4 times the mass of the Sun. The more precise modern figure comes out near 1.44 solar masses, and the exact value shifts a little, depending on what the star is made of and how fast it spins. But the headline is the thing to hold on to. There is a hard limit, and it is close to 1.5 suns. We call it the Chandrasekhar limit, and it is one of the most important numbers in all of astrophysics. Sit with what that means. Below the limit, a white dwarf is genuinely stable. It will slowly radiate its leftover heat into space over unimaginable spans of time, cooling and dimming, but its structure holds. In principle, it can last essentially forever, a cinder held open by quantum law long after the last fire has died. The rule does not tire, it does not leak, it just keeps refusing. But cross that limit, add even a little too much mass, and the same rule that shapes your body simply runs out of strength. The electrons cannot climb any higher, because they cannot move any faster, because nothing can outrun light. And so the floor gives way beneath the star. Here is what stops you cold about all of it. That ceiling was not found in a laboratory, or with a great telescope, or by a committee of famous men. It was found by a young man on a boat, scratching equations by hand while the ocean rolled underneath him. A number written in pencil during a weeks-long sea crossing turned out to be a universal ceiling. a hard limit on how much weight this single quantum rule can ever hold up, anywhere in the cosmos. The same principle that keeps your hand from passing through a table has an upper limit, and a 20-year-old found it before he had even arrived at university. The world did not thank him for it. When Chandrasekhar presented his result to the Royal Astronomical Society in London in early 1935, the most eminent astronomer of the age, Arthur Eddington, stood up and dismissed it. He called the idea a kind of stellar buffoonery. He could not accept that a star might have no stable ending, that gravity could ever truly win. He believed every star must settle into a peaceful white dwarf, and he used his enormous authority to wave the young man's work aside in front of the whole room. Chandrasekhar was humiliated. He was right, and he was humiliated, and it took the field years to catch up to him. Nearly half a century later, in 1983, he was awarded the Nobel Prize in Physics for exactly this work on the structure and limits of stars. The number held. The boy on the boat had seen further than the giant who mocked him. And notice how quietly ordinary the whole mechanism is. There is no exotic new force at the heart of a white dwarf. There is only the same exclusion principle you carry in your own fingertips. The refusal of electrons to share a state, scaled up until it is holding a dead sun open against its own crushing weight. The pressure in your hand and the pressure in that star are not cousins. They are the very same rule, working at wildly different sizes. That is what makes the Chandrasekhar limit feel almost personal. It is the point where a rule you rely on every second of your life reaches the edge of what it can do. For everything you will ever touch, the rule holds without effort. Push on a wall, and the electrons push back, easily, endlessly. But pile up mass, star upon star's worth of it, and you can finally find the place where the refusal breaks. It takes a dead sun and a little extra to get there. Yet the edge is real, and it is exactly where the young man said it would be. So imagine two white dwarfs side by side. One holds just under the limit. It sits there, cooling in the dark, stable for longer than the universe has yet existed. A quiet monument to the exclusion principle doing its patient work. The other holds just over the limit, and it cannot rest. Its electrons are already moving as fast as light will allow, and it is still too heavy, and there is nothing more they can offer. Gravity has finally met a star it can beat. What happens next is not a slow settling. It is a fall with no bottom in sight, because the one thing that could have caught the star has just been overwhelmed. The electron pressure that held up Sirius B, the pressure that could have lasted forever, is spent. Raw narration for Insert D. There is a moment in this story where the number itself goes on trial, and the young man who found it is made to stand beside it in a crowded room in London. His name is Subramanian Chandrasekhar. He is 19 years old when he boards a steamer bound from India to England in the summer of 1930, and somewhere on that long crossing, with the ocean sliding past and very little else to occupy the hours, he does the arithmetic that will one day carry his name. He's working out what happens to a dead star when you take the electrons seriously. Not as tiny points, but as particles moving faster and faster as they are squeezed until they begin to approach the speed of light itself. And when he follows that logic all the way down, a ceiling appears, about 1.5 times the mass of the sun. Above that line, the pressure holding the star open simply cannot keep up. You should sit with how small the tools were. No computer, no team. A pencil, some paper, a folding table on a ship, and a boy who has not yet turned 20. The number he draws out of that quiet is not a guess and not a mood. It is a hard edge written into the universe, and he can feel that it is real. He carries it to England the way you might carry something fragile in your coat, certain that when the right people see it, they will understand. For a few years, he sharpens it. He refines the calculation, folds in the relativity that makes the electrons behave, and by the winter of 1935 he's ready to lay it before the people who matter most. In January of that year he stands to present his result to the Royal Astronomical Society in London. He's 24 now. He expects, if not applause, then at least a fair hearing. He expects the room to weigh the mathematics and find it sound because it is sound. What he does not expect is the man who rises immediately after him. That man is Arthur Eddington. And to understand what happens next, you have to understand what Eddington was in that room. He was not just an astronomer, he was the astronomer, the most eminent figure of the age, the man who had measured the bending of starlight during an eclipse and confirmed Einstein to the world. When Eddington spoke about the insides of stars, the field listened, the way you listen to weather when you're already at sea. His authority was not a small thing. It was a kind of gravity in its own right, and it bent everything around it. Eddington rises, and he does not merely disagree. He mocks. He calls the idea a kind of stellar buffoonery, a physical absurdity. And he tells the room that there ought to be a law of nature to prevent a star from behaving in this ridiculous way. His objection is not really a calculation. It is a conviction. Eddington believed deep in his bones that every star must end its life quietly, as a white dwarf cooling forever into the dark. The thought that some stars might have no stable ending at all, that gravity might win completely and crush the matter past any rescue, struck him as monstrous, so he refused it, and he did it in public, standing over the younger man, with the full weight of his name pressing down. Picture what that does. The careful numbers, worked out by hand on a swaying ship, set down in front of the most important people in the field, and then, in a matter of minutes, wiped away like chalk dragged off a board by the flat of a hand. Not disproven, not even truly answered, just erased by the sheer authority of the person doing the erasing. The board goes blank, the room moves on. And the correct answer is left sitting there in the dust at the bottom, still correct, still true, and treated as if it had never been written at all. You can guess how the community responded because you have seen how people respond when a giant speaks. They deferred. Not all of them, and not because they had checked the mathematics and found Eddington right. They deferred because he was Eddington, and the young man was young, and it was easier and safer to assume the eminent one knew something the newcomer did not. The result was pushed to the margins. For years the mass limit was something spoken of carefully, hedged, half-believed, because the field's most powerful voice had declared it nonsense. A true thing about the universe was slowed down, held under, kept from its proper place, by nothing more than the shape of one man's certainty. And here is the part worth carrying with you as you drift towards sleep. Chandrasekhar was right. The mathematics did not care who mocked it. The electrons really do speed up as they are crushed, really do approach the speed of light, and really do reach a point where they can no longer push back hard enough. The ceiling he found on that ship was real, and it was there all along, waiting for the field to catch up to the boy who had already seen it. It took decades. But the number outlived the objection, the way a true thing usually does, quietly, without needing to win the argument in the moment. In 1983, nearly half a century after that humiliation in London, Chandrasekhar was awarded the Nobel Prize in Physics for this, and his related work on the structure and evolution of stars. The man who'd been laughed out of a room as a young scientist lived to see the ceiling bear his name and hold up under every test. The pencil marks that Eddington swept off the board turned out to be a permanent feature of reality, and the whole science of what happens to dying stars now rests on them. There is a small honesty worth keeping even here. The exact value of that ceiling is not a single frozen digit. You will hear it as about 1.5 times the mass of the Sun, and you will also hear the more precise figure of roughly 1.44 solar masses. The difference is not a flaw in the idea. It comes from the details, what the dead star is actually made of, how fast it is spinning, the fine composition of the matter being crushed. The precise number shifts a little with those conditions, and astrophysicists still refine it. But the edge is unmistakable. There is a line. It is somewhere close to 1.5 suns, and it does not move very far no matter how you argue. What the whole episode really teaches is something about physics itself, something quieter than any single number. Eddington wanted there to be a law that forbade collapse. He wanted the universe to be tidy, to guarantee every star a gentle ending, and the universe declined. It offered no such law. It allowed the ceiling to exist precisely because it allowed something to lie above the ceiling, some further state that Eddington could not stomach imagining. The resistance he felt, that instinctive refusal to believe gravity could keep winning, was not a flaw in his intelligence. It was fear of what the honest answer implied. Because the honest answer is that the rule holding a white dwarf open is not infinite. It has a strength, and that strength has a limit, and past the limit the rule that gives your body its shape simply runs out of room to fight. So the debate was never really about a boy and a great man, though it looked that way in the room. It was about whether the cosmos is allowed to have a place where matter is pushed past the last thing that can hold it. Chandrasekhar said yes, and drew the line with a pencil on a ship. Eddington said no, and wiped it off the board with his name. And the universe, patient as ever, sided with the pencil. The line is there. You can feel where the whole story has been leaning all this time toward that edge, toward the question of what happens when the electrons are finally overwhelmed and there is nothing left for them to do but give way. The answer waits just on the other side of 1.5 suns, and it is stranger than anything Eddington was willing to picture. Cross that line, about 1.5 times the mass of the sun, and the electrons finally lose and something far stranger takes their place. Cross that line, about 1.5 times the mass of the sun, and the electrons finally lose and something far stranger takes their place. When a dying star's core pushes past the Chandrasekhar limit, gravity wins the argument it had been having with the electrons, and it does not stop there. The electrons are crushed so hard that they are driven into the protons themselves. The two merge. Each pairing becomes a neutron, and a ghostly particle called a neutrino that streaks away carrying energy with it. In the space of about 1 second, the core of a great star converts almost entirely into neutrons, a ball of them, a single continuous knot of neutral matter where atoms used to be. And then, once again, the falling stops. Not because gravity has softened, gravity has only grown stronger. The collapse halts because the neutrons refuse to share. This is the very same Pauli Exclusion Principle you have been following all night, the same quantum rule that gave your fingertip its shape now making its second stand. Neutrons are fermions too. No two of them can occupy the same quantum state. Pack them close enough and they push back with a pressure of their own, neutron degeneracy pressure, the same refusal expressed by particles packed vastly tighter than any electron ever was. If this is your first night drifting through deep space drift, consider following along, and a like helps these quiet journeys reach others. You can find us on Spotify too, that is all. Now settle back, and let us look at what the neutrons built. Consider the object that results. Take somewhere between 1.5 and 2 times the entire mass of the sun, not a portion of it. More mass than our whole star, the star that holds 8 planets in their orbits, across billions of miles. Now compress all of that into a sphere about 12 kilometers across, which is roughly 7.5 miles. That is the size of a city. You could drive across it in a few minutes on an ordinary highway, if a highway could exist there, which it could not. Everything a sun contains, folded down to the footprint of a town. The numbers only grow stranger the deeper you go. The center of a neutron star reaches a density 5 to 10 times that of an ordinary atomic nucleus. Think about what that means. The nucleus is already the densest thing in normal matter, the tiny pit at the heart of the atom that holds nearly all its weight. A neutron star is denser than that throughout, for miles, and the density is not uniform. From the thin surface down to the buried core, it climbs by about 14 orders of magnitude. That is a factor of 100 trillion. The outer skin and the deep center are as different from each other as a wisp of air is from solid steel, and both belong to the same object, stacked one atop the other in the space of a few miles. Here is the figure people remember, and it is worth sailing slowly, so let it settle. Imagine a single teaspoon, an ordinary teaspoon from a kitchen drawer. Fill it not with sugar, but with matter scooped from the inside of a neutron star. That teaspoon would weigh, on the surface of the Earth, roughly 1 billion tons. 1 billion tons or more. The estimates vary from source to source, and some run higher still, but 1 billion tons is the honest rounded shape of it. That is heavier than Mount Everest. A whole mountain, the tallest on the planet, pressed into a volume smaller than a sugar cube. A city crushed into something you could balance on the tip of a spoon and could never ever lift. You could not lift it because nothing you know could hold it. It would tear straight through the spoon, through the table, through the floor, through the crust of the Earth, falling toward the center because no ordinary material has the strength to resist that weight. The only thing in the universe that keeps a neutron star from crushing further is the neutrons themselves, standing on the same principle Pauli wrote down in a single page in January of 1925. Refusal made physical, holding up a mountain in a teaspoon. For a long time, no one knew these objects were real. They were a prediction on paper, a thing the equations allowed but no telescope had ever seen. That changed on the night of November 28, 1967, in a field outside Cambridge, England. A graduate student named Jocelyn Bell Burnell was combing through data from a radio telescope, and this was not a dish. It was a sprawl of poles and cables covering acres of ground, strung together from about 120 miles of wire, much of which she'd helped build by hand. The signal arrived on long rolls of paper, ink traced by a moving pen, miles of it. And in that endless scrawl she noticed something that did not belong, a small, repeating smudge, a bit of scruff she later called it. Most people would have dismissed it as interference from a passing car or a faulty wire. She did not. She went back and looked closer, and she found that the signal was pulsing with impossible regularity. A pulse, then silence, then a pulse again, every 1.337 seconds, over and over, more precise than a clock. Nothing natural was supposed to keep time like that. The universe is not a metronome. The regularity was so perfect that the team half seriously wondered whether it was a message. Her supervisor, Anthony Hewish, gave the source a playful label, LGM-1, standing for Little Green Men, on the off chance they had stumbled onto a signal from another civilization. They had not. Within weeks, Bell Burnell found more of these ticking sources, scattered across different parts of the sky, and it became clear no alien would be broadcasting from so many places at once. What she had found was something the equations had whispered about for decades: a neutron star spinning. The discovery was published in the journal Nature on February 24, 1968, and it changed astronomy forever. We call these spinning neutron stars pulsars, and once you understand how they work, the ticking makes a strange kind of sense. A neutron star is not a quiet thing. When a great star collapses, it spins up, the way a skater pulls in her arms and whirls faster. All that rotation, concentrated into a ball only miles wide, becomes a blur. Some pulsars turn once every few seconds, others turn hundreds of times every single second. A point on the equator of the fastest of them moves at a real, meaningful fraction of the speed of light, whipping around a city-sized ball so quickly that the numbers stop feeling like physics and start feeling like something out of a dream. And these stars have magnetic fields of staggering strength, funneling radiation out through their two magnetic poles in tight beams. If those poles do not line up with the axis the star spins around, and they usually do not, then the beams sweep through space like the light of a lighthouse. Round and round they go. Each time one of them happens to point at Earth, our telescopes catch a flash. Then the beam swings away, and we catch nothing until it comes around again. That is the pulse. That is the ticking Jocelyn Bell Burnell saw. Not a message, A beam of radiation from a spinning corpse, sweeping across the miles of empty space between us like a hand passing over a candle flame. The gravity near one of these objects is so extreme it bends the very light the star gives off. If you could somehow stand near a neutron star and survive, you would see something no ordinary sky can show you. The star's own gravity curves the path of its light so severely that the far side of the sphere would appear to wrap around the near side. You would see more than half of it at once. The back of the ball folded forward into view as though the object were peeling itself open for you to look inside. Space itself is warped that tightly. Light no longer travels in the straight lines your eyes were built to trust. Step back now and consider what neutron degeneracy pressure actually is in the grand accounting of a dying star. When the biggest stars die, they do not all end the same way. Some leave behind a neutron star, this city of packed neutrons, ticking and spinning for millions of years. Others leave behind a black hole, a region where matter has vanished entirely behind an event horizon, a place from which not even light returns. What decides which fate a star meets? Where is the line? The line is exactly this. Neutron degeneracy pressure. It is the physical mechanism that separates a stellar corpse that survives from a stellar corpse that disappears. If the collapsing core is light enough, the neutrons hold. Their refusal to share a quantum state generates enough outward pressure to stop gravity in its tracks, and what remains is a neutron star, dense and strange but stable. It will sit there in the dark for ages, cooling slowly, spinning down over eons, a monument to a rule written on paper long before anyone knew stars could die this way. But if the core is too heavy, the neutrons cannot hold. The pressure is not enough. Gravity keeps pulling, and the whole thing continues its fall past the point of no return, wrapping itself in an event horizon, becoming a black hole. So this quiet quantum rule, the exclusion principle, is doing something almost unbelievable when you say it plainly. It is the difference between existence and disappearance. It is the last wall between a star that leaves a body behind and a star that leaves only a hole in space where a body used to be. And it is the same wall, exactly the same, that stands inside you. The reason the electrons in your hand do not collapse into your bones is the reason a white dwarf holds up a dead sun in a sphere the size of the Earth, and it is the reason a neutron star holds up nearly 2 suns in a sphere the size of a city. One principle, one refusal, scaled from the tip of your finger all the way up to the densest stable matter in the known universe. The neutrons in that city-sized ball are obeying the very same law that gives your body its volume tonight. They are simply doing it under a weight your imagination can barely hold. There is a poetry in how far this rule reaches. It began as a small correction to a model of the atom, a way to explain why electrons stack into neat shells instead of all crowding the lowest rung. It became the reason the periodic table has the shape it has. It became the reason the ground beneath you is solid. And then, in the death of stars, it became the thing that decides whether a collapsing core becomes a spinning beacon or a silent abyss. The same word, refusal, answers all of it. No two of these particles will occupy the same address, and from that single stubbornness, whole objects are built and whole fates are sealed. So picture it one more time as you lie there. A ball of neutrons, hardly wider than a city, holding the mass of 2 suns spinning hundreds of times a second, its light folding around itself, its surface 1 billion tons to the teaspoon, all of it braced against total collapse by the quietest rule in physics. It is held for the entire age of that star. It may hold for a great deal longer. Neutron degeneracy pressure is a formidable thing, the second stand of the exclusion principle, and it does not give way easily. You can hear one of these limits being reached now if you build the right ears for it. In August of 2017, for the first time, we did. Two neutron stars have been circling each other for ages in a galaxy called NGC 4993, about 130 million light-years from where you're lying tonight. That is when they finally fell together. The signal from that fall is now called Jubelsven 817. It was the first ripple in spacetime ever traced back to a collision of two neutron stars. The two stars were not large by cosmic standards. Each one held somewhere between 1.17 and 1.60 times the mass of our Sun. Together they came to roughly 2.74 solar masses, folded into two balls no wider than a city apiece. For about 100 seconds, detectors on Earth felt them spiral inward. The tone rose in pitch as they closed the gap, a slow climb that quickened into a rush, and then it stopped. About 2 seconds after the stars touched, a burst of gamma rays swept across the solar system. The universe had, in a sense, made a sound, and we had finally learned to feel it. Think about what it takes to notice that. The waves stretched and squeezed the whole planet by less than the width of a single proton. 2 observatories in the United States and 1 in Italy caught the same faint tremor within milliseconds of one another. From the timing alone, astronomers worked out a patch of southern sky and pointed roughly 70 telescopes at it. What they found there is the part that reaches all the way down to your hand. When the two stars met, they did not simply settle into a quiet ball. The collision flung a shell of matter outward, a spray of loose neutrons torn free from the wreck. This is the moment astronomers call a kilonova, and it is where something very ordinary was born. Free neutrons are greedy things. In that hot, crowded spray, atomic nuclei swallowed neutrons faster than they could break back down, a process physicists call rapid neutron capture, or the R process. Layer by layer, in less than a second, light nuclei were built up into the heaviest elements nature makes. Among them were gold and platinum. Those newborn nuclei were unstable, and as they decayed they gave off heat and light. Over the following days the glow shifted from a bright blue to a deep infrared red, exactly the fading signature a kilonova should leave. For the first time, people watched heavy elements being forged in real time in a fireball roughly the size of the solar system. Careful estimates suggest that one event may have made many times the mass of the Earth in gold alone. Not gold already sitting in the ground somewhere. Gold made that week in front of the lens. Now think about the object left behind at the centre. Add the two stars together and you have close to 2.74 solar masses pressed into a single place. That is well past the ceiling neutron degeneracy pressure can hold. It is the same Pauli rule as before, neutrons refusing to share a state, only now it is being asked to carry more than it can bear. For a moment the merged body spun as one furious mass, held up partly by that stubborn quantum pressure and partly by the sheer speed of its own rotation. It did not last. The evidence suggests the remnant survived only tens to hundreds of milliseconds before its own weight won, and it folded away behind an event horizon, becoming a black hole. The exact stopwatch is still argued over. Some readings of the data favour a slightly longer stay, some a shorter one. What almost no one disputes is how brief the pause was. A single heartbeat, and then nothing that light can escape. So most of G Brosendon 7 or Assistant 7 ended its life as a black hole, but not all of it left. The shell it threw off kept going, cooling and spreading, seeding the space around that distant galaxy with fresh heavy metal, and here is the quiet thing to carry with you. The gold in a wedding ring did not form on Earth. Our planet is far too gentle a furnace to make it. Every atom of gold anyone has ever held was forged in a cataclysm like this one, in the spray of colliding dead stars, long before the Earth existed at all. A plain band on a finger is a direct souvenir of a collision older than the ground it rests on. When you close your fingers around a small ring of gold, it feels warm, warmed by your own skin. But it is easy to imagine another warmth folded inside it, the warmth of the fireball where it was made, the last bright flare of a place where quantum pressure fought gravity and lost. That warmth travelled an enormous distance to reach a hand. The atoms drifted for billions of years through the dark. They gathered slowly into a cloud, and the cloud collapsed into a sun and its planets, and on one of those planets there grew rivers and cities, and eventually jewelers. Every heavy thing solid enough to weigh in your palm carries that same history. The iron in your blood, the calcium in your bones, and above all the gold and the platinum which we prize precisely because they are so rare, so difficult to make that only the death of a neutron star will do the job. For most of a century this was a good guess and little more. Astronomers strongly suspected that the heaviest elements came from neutron star collisions, but no one had ever watched one happen. GW 178887 turned the guess into a record. The gravitational wave told them that two neutron stars had merged. The changing colours of the fading light told them that gold and platinum were being minted in the debris. The two separate stories lined up perfectly. In a single night, a long-standing question about where the heavy metal of the world comes from was answered by an event 130 million light-years away felt on the ground as a shiver smaller than an atom, and all of it turned on that same limit, reached in the deepest part of the collision. Two neutron stars, each already a city of matter held rigid by neutrons that would not share a state, had spent an age spiralling closer and closer. Each one, on its own, was stable and patient, capable in principle of lasting nearly forever. It was only when they became one, only when their combined weight crossed the ceiling, that the pressure holding them apart finally gave. For a few hundred milliseconds a single object teetered on the exact edge of what neutrons can hold up, and then it slipped over that edge. A lone neutron star can feel like the most permanent thing you could ever imagine. 1 billion tons pressed into a single teaspoon, held together by a rule that no experiment has ever once caught breaking. Left undisturbed, it would coast through the dark, spinning quietly, for longer than the present age of the universe. It is the closest thing to unbreakable that ordinary matter can become, and yet even neutrons, packed 1 billion tons to the teaspoon, turn out to have a breaking point of their own. And yet even neutrons, packed 1 billion tons to the teaspoon, turn out to have a breaking point of their own. There is a line in the sky you can only cross once. Push a dead star past roughly 2 times the mass of the Sun, and the same rule that once held electrons apart and then held neutrons apart finally runs out of room to stand. Gravity has been patient this whole time. It has waited through every earlier refusal. Now it wins. Below that line, a neutron star holds. The neutrons refuse to share a quantum address, and that refusal becomes a pressure, and that pressure props up a whole city of matter against its own crushing weight. Above that line, the refusal is no longer enough. The neutrons are still saying no. Gravity simply stops listening. Watch what happens when it does. The star does not gently deflate. It falls inward at a real fraction of the speed of light. In a handful of milliseconds, a ball of neutrons about 7.5 miles across collapses toward a point, and an event horizon closes over it like water over a dropped stone. A black hole is born out of what used to be a star. And here is the strange part. The Pauli Exclusion Principle never actually failed. The neutrons never once occupied the same state as their neighbours. Gravity did not break the rule. It simply overwhelmed the thing the rule was holding up, and buried it behind a horizon where no light and no answer can ever come back out. So there is a ceiling, and past the ceiling there is a black hole. But physicists have long wondered whether something hides in the narrow gap between the two. A last exotic state of matter, denser than a neutron star and still not quite a black hole. That idea has a name, a quark star. Sometimes a strange star. To understand it, you have to look inside a single neutron first. A neutron is not a solid pellet. It is 3 quarks, bound so tightly by the strong force that under ordinary conditions they can never leave. 2 down quarks and 1 up quark, locked in a cage they cannot escape. In a normal neutron star, the neutrons are crushed shoulder to shoulder, but each one still keeps its own quark sealed inside. Now push harder, squeeze past the density that even a neutron star knows. In theory, the cages break. The walls between neutrons dissolve, and the quarks spill out of their individual prisons into one continuous sea. They are no longer sorted into neutrons at all. They flow together as a single degenerate fluid, a soup of loose quarks filling the entire star from centre to surface. Notice what holds that soup up. The very same rule. Quarks are fermions too. They obey the exclusion principle exactly as electrons and neutrons do. So when the neutrons come apart, the quarks inside them still refuse to share a state. The line of defense does not vanish. It just retreats one level deeper, down to the quarks themselves, and makes it stand there. Some versions of the idea go further still. If a fraction of those quarks convert into a heavier kind, the strange quark, the whole mixture might settle into something even more stable than ordinary matter. That is the strange star. A star made of strange quark matter, quietly holding a shape that nothing else in the universe can hold. A quark star would be smaller than a neutron star and denser. A neutron star runs somewhere around 20 to 25 kilometers across, a little over 12 to 15 miles. A quark star, if it is real, might be only 10 to 16 kilometers wide, while carrying as much mass as a neutron star or more. Picture taking a city that has already been compressed down to almost nothing and then wringing the last empty space out of matter itself. Now hold one fact steady in your mind. No quark star has ever been confirmed. Not a single one. Astronomers have found a few unusually compact objects, stars that seem a touch too small or too dense for the standard neutron star recipe, and a handful of those have been proposed as candidates. But every candidate has other explanations that fit just as well. This is a hypothesis, not a discovery. The quark sea may be real, glowing somewhere out in the dark right now. It may also be a beautiful idea that nature simply never chose to build. We do not yet know which. What we can watch, directly, is the moment a star gets pushed over the edge. In August of 2017, we felt one for the very first time. Far away, two neutron stars had been circling each other for ages, drawing closer by inches, then by feet, then by miles with every orbit. Each one weighed somewhere between about 1 and 1.6 times the mass of the Sun. Together, close to 2.74 solar masses. At the very end, they were whirling around each other hundreds of times a second, and then they touched. The collision sent a shudder through space-time itself. That shudder crossed the universe and washed over the Earth as a gravitational wave, a real ripple in the shape of space, stretching and squeezing everything it passed by less than the width of a single proton. We caught it. The signal was named GW von 17, and it was the first time we ever traced a gravitational wave to two neutron stars falling together. But the wave was only half the story. Where the two stars met, matter did something almost beyond description. For a fraction of a second, the merged core became denser than anything in the observable universe short of a black hole, a hypermassive knot of neutron matter spinning furiously, far heavier than any neutron star has a right to be. It teetered there, balanced on the exact edge of what the exclusion principle can still hold. Think of the rope again. All the way up this story, matter has been a rope pulled taut against gravity. Electrons, then neutrons, then perhaps quarks, each fibre straining. In that remnant, the rope was fraying under one final strain. Every strand of degeneracy pressure stretched to its absolute limit at once, all of them pulling and none of them slack. It did not hold for long. The evidence suggests the remnant survived only tens to hundreds of milliseconds before it lost the fight and collapsed into a black hole. The exact timeline for that particular merger is still debated. Some analyses argue it lingered a little longer than the first estimates, but the ending itself is not in doubt. Gravity won that round, the way it always eventually does, and out of the wreckage came something you can hold in your hand. As the stars tore apart, they flung a spray of neutron-rich matter into space. In that fireball, atomic nuclei swallowed loose neutrons faster than they could decay. building heavier and heavier elements in a matter of seconds. Gold, platinum, heavy metals scattered outward to cool and drift and one day settle into new worlds. The glow of that process, a kilonova, was seen by telescopes across the Earth within hours of the wave arriving. So the gold in a wedding ring may be a direct souvenir of a night like that one. Forged in the instant degeneracy pressure was losing its last fight, out of matter balanced on the knife edge between a star and a hole punched in space. You may carry on your own hand the evidence of the rule bending as far as it can possibly bend. And that is what makes the final fact of tonight so strange. Through all of this, across white dwarfs and neutron stars and merging remnants, and the theorized soup inside a quark star, the exclusion principle has never once been caught breaking. Not bent, not broken. Overwhelmed, yes, when gravity buries it behind a horizon, but never violated. Nowhere, at any density we can reach or measure or observe, has a fermion ever been shown to slip into a state that another fermion already held. The rule that gives all matter its shape has a perfect record, and no one is entirely sure why. That mystery has driven one of the quietest hunts in all of science. If the principle can break, even a little, even once in an unimaginable number of tries, it should leave a faint fingerprint behind, a flash of light that has no right to exist. So physicists went looking for exactly that flash. They went underground to find it, deep beneath a mountain in Italy, shielded from the noise of the sky by a full mile of solid rock. They have been listening down there patiently for years. The timing carries its own quiet weight. In 2025, this rule turned 100 years old. It was back in early 1925 that Wolfgang Pauli first wrote it down. A single careful sentence meant only to explain why the electrons in an atom keep their distance from one another. A century later, that same sentence stands behind the shape of your body, the solidity of the ground beneath your feet, and the survival of every dead star that did not become a black hole. And to mark the anniversary, the search for one crack in it only grew more careful, more sensitive, and more stubborn. You will step inside those experiments soon, into the copper and the cold, and the exact way a person hunts for a law of nature breaking itself. For now, hold only the result. After all of that effort, the detectors have returned silence, a clean, complete, unbroken silence. Sit for a moment with how remarkable that is. Physicists have searched for one flaw in this rule harder than they have searched for almost anything else in all of physics. They have built machines whose only purpose is to catch it failing. They have run those machines for more than a decade under a mountain, and matter has never once handed them a single crack. The rule holds to a precision so extreme it borders on the absolute. And still, at the very deepest level, no one can prove from first principles why it has to be true. We know, beyond any doubt, that it is. We simply cannot yet say why. Consider what it takes to hunt a rule that never breaks. You cannot set a trap for it in the open air. The sky rains down cosmic particles by the billion, and each one can fake the very flash you are looking for, so you go underground. In the Apennine Mountains of central Italy, beneath nearly a mile of solid limestone, there is a laboratory called Gran Sasso. The rock above it swallows cosmic rays and cuts them down by roughly a factor of 1,000,000. What reaches the detectors down there is close to silence, and silence is exactly what this experiment needs. The experiment is called VIP2, and its whole name is a small joke about its purpose. VP stands for violation of the Pauli Exclusion Principle. It is a machine built to catch the rule cheating. If you want to follow just one idea tonight, follow this one, and if these long quiet documentaries help you rest, a like or a subscribe helps more people find them, and they wait for you on Spotify too. Here is how the trap works. You take a strip of copper, and you push a strong electric current through it. That current is a river of fresh electrons pouring into the metal, electrons the copper atoms have never met before. Every one of those newcomers wants to settle into the lowest, most comfortable energy it can find. but the low seats inside each copper atom are already taken. The innermost orbital is full, occupied by its lawful pair, spun in opposite directions, closed. The new electron is forbidden from dropping in. That is the rule. Now imagine just once the rule slips. A new electron ignores the sign and falls into that full inner shell anyway. It cannot stay at the outer energy it arrived with. It tumbles down into a lower rung it was never allowed to touch. And when a charged particle falls to a lower energy, it pays for the trip by throwing off light. In copper, a jump like that would release an X-ray of a very particular energy, not just any glow, a specific color of X-ray at a specific number of electron volts, slightly shifted from the normal, legal X-rays copper is allowed to make. That tiny shift is the whole game. A forbidden transition lands at an energy the ordinary rules can never produce. So the detectors sit and watch the copper, sorting every X-ray by its energy, looking for a flash in that one impossible slot. A legal atom cannot make that light. Only a broken rule can. If even one clean flash appeared in that forbidden window, it would be the first crack ever found in 100 years of matter obeying. So the physicists wait. This is the part that is hard to picture at a human scale. It is not a quick experiment. It runs for years quietly in the dark under the mountain. The detectors listen the way you might press an ear to a mile of stone, holding your breath for a single tap from the other side. Season after season, the current keeps flowing. The copper keeps its full inner shells, and the tally of forbidden X-rays keeps reading the same number. 0. Over more than a decade of listening, the answer never changed. The result was reported in the journal Scientific Reports, work that carried into 2025 and 2026. VIP2 set the strongest limit ever measured on this kind of violation for electrons inside ordinary bulk matter. Put it plainly, if electrons break the exclusion principle at all, they do it fewer than about 2 times in every 10,000 trillion attempts. Written out, that is 2 in 10 followed by 42 zeros. And across all of that, not one violation was seen. The rule held perfectly, down to a precision almost impossible to hold in your mind. Catalina Curzianu, a physicist with Italy's National Nuclear Institute who has led this hunt, framed what that silence means for anyone hoping to rewrite physics. Any new theory that wants to replace or extend quantum mechanics has to reproduce the exclusion principle, and reproduce it with extraordinary precision. Even a violation too small to notice in a laboratory would ripple outward. It would leak into the structure of every atom, and from there into the lives of stars. A rule this exact leaves almost no room for a new idea to hide, and it closes doors on several ideas that were hiding. For years, theorists have played with particles they call quants. Imagine things that would sit somewhere between the two great families, not quite obeying the exclusion of fermions, not quite free like bosons. The VIP2 result squeezes those quant models into a corner. It also presses hard on theories that give the electron a secret inner structure, some hidden machinery underneath what looks like a simple point. And it constrains certain approaches to quantum gravity, the ones that predicted the rule might bend by a hair at the smallest scales. The silence under the mountain tells all of them the same thing. If you bend the rule, you bend it less than this, or you are wrong. While the mountain listened for a violation, a laboratory in Paris did something almost opposite. It photographed the rule-keeping. In the spring of 2025, a team led by Tarek Yefsar at the Castler Brossel laboratory took hundreds of lithium atoms, the light and simple isotope lithium-6, and cooled them until they were a whisper above absolute zero. At that stillness, the atoms behaved as a crowd of fermions must. They could not all sink to the bottom. Forbidden from sharing a state, they stacked upward, filling one level, then the next, building a structure the physicists call a Fermi sea. What made it remarkable was that you could see it. The cloud held a sharp edge, a clean outer surface, atoms arranged in shells exactly the way electrons arrange themselves inside a single atom, only here blown up to a size a camera could catch. For the first time, the exclusion principle was made directly visible, a giant atom's worth of orderly stacking imaged on a screen. One machine hunted the rule breaking and found nothing. The other simply showed you the rule at work, patient and exact in a puff of frozen gas. There is one more place people go looking for a loophole, and it is worth clearing away before the anchor. Superconductors. In a superconductor, electrons pair up. Two of them join into what is called a Cooper pair, and pairs like that behave like bosons, the sociable family, so they pour together into one shared state and carry current with no resistance at all. It looks, at a glance, like a room full of fermions finally agreeing to share. Leon Cooper won a share of the 1972 Nobel Prize for explaining it. But nothing is broken there. Look inside a pair and the two electrons are still fermions, still keeping their distance from every other electron in their own private accounting. The pair is simply large and loose and blurry enough that its tiny internal differences stop mattering to the crowd. The rule is not suspended. It is respected quietly, underneath a costume. Every apparent escape, when you look closely, is the rule keeping itself. So this is where the search stands. Under an Italian mountain, a machine listened for a decade and heard nothing. In Paris, a camera watched the rule stack atoms into shells you could photograph. In every superconductor that seemed to cheat, the electrons were obeying all along. After 100 years of looking, no one has ever caught matter breaking the one rule that lets it exist. After 100 years of looking, no one has ever caught matter breaking the one rule that lets it exist. Not once, not anywhere, not in the coldest lab or the densest star. The rule simply holds, and now, near the end of the night, it is worth setting the numbers down and resting in the plain shape of the thing. Think about what is actually happening in the space around you. The floor beneath you is holding, the walls are keeping their edges. Your own body has a size, a volume, a shape that stays where you left it. None of that is guaranteed by weight or by will. It is guaranteed by a refusal. Trillions upon trillions of electrons, packed into every surface you can see, are quietly declining to share a single quantum address. That refusal is the reason anything has room to be. Let your attention drift down to your own hand. Feel its weight wherever it rests, on the blanket or on the sheet or on the mattress. It feels solid. It feels simple. But almost all of it is empty. Scale one of its atoms up to the size of a stadium, and the nucleus would be a single pea at the centre, with nothing but open space stretching out to the seats. Your hand is very nearly nothing at all, and yet it holds its shape. It does not sink through the bed. It does not fall in on itself. The reason is that the electrons inside it will not stack into the same lowest place. Squeeze them, and they do not surrender. They climb into higher and higher states, and that climbing pushes back with a real pressure, an outward firmness that owes nothing to heat and nothing to charge. When your palm presses the blanket, nothing truly touches. The electron clouds simply refuse to overlap, and you feel that refusal as the soft, ordinary solidity of a resting hand. Now let the same idea widen. The same refusal that gives your hand its volume is holding up dead suns. A white dwarf is the mass of the sun folded into a ball the size of the Earth, kept from collapse by nothing but electrons that will not be pushed into filled seats. A single spoonful of it would weigh as much as an elephant. Push past roughly 1.5 times the sun's mass, and even that grip fails, and the star falls further into a city of neutrons where a single teaspoon weighs about 1 billion tons, more than a mountain. There, the same rule stands again, one last wall between a spinning corpse and a black hole. It is one rule. That is the quiet astonishment of it. The firmness in your fingertip and the wall inside a neutron star are the same law, written once, obeyed everywhere. From the softest thing you can imagine to the densest thing short of a black hole, Matter keeps its shape by declining to share, and no one can fully say why. That is the strange heart of the whole night. Physicists can prove the rule follows from deeper theory. They can measure how faithfully it holds down to fewer than 2 possible slips in numbers so vast they have 43 zeros. They can build detectors a mile under a mountain and listen for years for a single forbidden flash and hear only silence. But ask them at the very bottom, for the plain reason nature insists on this, and even the greatest of them will tell you honestly that they cannot give a simple answer. The rule is perfectly kept and not fully understood. That is allowed to be true at the same time. So here is the shape to carry into sleep. The only thing standing between you and collapse is also the only thing giving you a body at all. Take the refusal away, and the floor and the walls and your resting hand would fall inward toward the size of a grain of sand, and the reason you have volume would vanish in the same instant. The rule that could undo you is the rule that draws your outline. It is not a threat. It is the shape of being here. You do not have to hold any of this. Let the numbers go soft. Let the white dwarfs and the neutron stars drift back out to where they live, far away and unhurried, spinning slowly in the dark. You do not need the names or the dates. They will keep without you. Feel your hand again, the quiet weight of it. Solid and mostly empty and entirely yours. Every electron in it is doing its one small job right now, and it will still be doing it while you sleep and when you wake and long after. It asks nothing of you. It simply holds. The stars overhead are held by it too. The ground you cannot see beneath the building is held by it. The whole slow architecture of ordinary things, the reason a table stays a table and a body stays a body, rests on that same patient refusal to overlap. It has never once failed. There is no record anywhere in 100 years of looking of it letting go. So let your breathing slow. Let the room settle around you. Somewhere out there a dead star is being held up by the same law that is holding you together, and neither of you has to do a thing. The rule keeps itself. Nothing is being asked of you now. The floor will hold. The walls will hold. Your own quiet shape will hold, kept whole by trillions of small refusals that will never rest, so that you can. Let it all grow still. Let the last of the numbers fade into the dark. You are held and you are shaped, and you are exactly the size you're meant to be. Sleep well tonight. Good night.